Hello and welcome back to the Code Athlete. This evening we will have a look at round 1B from Google Code Jam 2022. I already advanced to round 2 in round 1A, which was 2 weeks ago. I've uploaded the video, so have a look at that one. Otherwise, if this video helps you understand your solution better or understand how to approach problems, feel free to leave a comment. I always appreciate any likes and subscribes, of course. It helps the channel out. And now I will only have a look at round 1B to practice and to help you maybe understand how the problem could have been solved. If you had any problems, I hope in any way that you managed to advance to round 2. Otherwise, I hope you participate in round 1C. So that's your third chance to advance. And let's dive right into it. I'm 50 minutes late, or now 60 minutes already late. But again, I'm not competing here really against anyone anymore. We have again a pancake problem. Nice. Okay, so I guess in this example we have the deliciousness level 1, 4, 2, 3. We can serve from left to right. And we want to maximize the number of paid pancakes. So let's first sell this pancake because it has the lowest level. Then we have 4, 2, 3 left. If I now serve 4, then 2 and 3 will be unpaid because 4 was the most delicious. So I will serve 3. Now I have 4 and 2 left. I can't serve 2 because it's in the middle between 4 and 3, and I only am allowed to serve from the left or the right. So I serve 1, then 3, I get 2 paid pancakes. The 2 then won't be paid because 3 was already larger, and then I will serve 4, which will get paid. So I guess this is a test case where we get 3 paid pancakes, yes. Here they're all the same, so I will get paid all of them because it's lower or equal the condition for a paid pancake. Now, what is the strategy? I think it is just greedy taking the lower number from the front or the back. Yes, I'm pretty sure it's greedy. So in this case, for example, if I would start with this number, I immediately have all the other pancakes unpaid. So I will start with a 7. Then I have 1 and 1 million or so. So yeah, I can then take the 1, but it will be unpaid because I already had the 7. Then I take the 3, which will be unpaid, and then I will take this one, which will be paid again. So I have 2 pays. I think greedy should here be the optimal solution always. And we can iterate over all numbers because 10 to the power of 5 times 100 test cases is easily manageable. So let's implement this. The first line gives us n, and then we have the di deletionist values, which we resize to n. V of LL is, by the way, in my abbreviation, V sounds like vector because I mostly use it as vector, but it actually is, or is it? No, I'm not sure. I've changed that maybe in the past. Oh, it's a vector. Okay, so maybe I want to have a Deque to pop from front and from the back. The deletionist values start from 1, so I can set d min to 0 in the beginning, and that should be fine. While there are still pancakes left. Front, smaller, then back. Result, add the front bigger or equal to d min. Then we set d min to maximum of the new value. And we pop front. Else we do everything from the other side. And this should be it. Yep. Why is it not allowing me to? Sorry, yes. So, because I took part in round 1A and I actually advanced to round 2, I'm not able to submit my solutions right now. So I will do this in the end of the competition to check that all my solutions are correct. Right now I just have the indication that the test set went through and it's the first problem, so it's really a matter of if this is fast enough or not, but I'm pretty sure it is. And the solution should be right. So yeah, sadly I cannot check it. I'm not sure. You have not attempted this problem, yes, but I think that is the reason why I don't have any upload options here, because I already advanced. I'm pretty sure that's it. So we'll just go to problem 2, and you have to skip to the end of the video. Again, I make chapters everywhere for which part of my video is the solution finding process, which part is the implementation process, so you can skip certain parts. And now you will see a chapter where I check all my solutions after the competition. So So let's put this aside and look at problem B, controlled inflation. So in this case, I have 3 customers and they each bring 3 products. First customer brings pressure values of, so products with pressure values of 30, 10 and 40, then 20, 50, 60 and 60, 60, 50. And I can rearrange these 3 numbers in any order. Then I can rearrange these 3 in any order, these 3. And I have to determine the minimal number of button presses I can achieve. And in this second case, I have actually 5 customers, each bringing 2 products. So what is if I have 1 customer? What is the optimal way to do it? I think the optimal way would be just to sort them and go from lowest to highest. So maybe I should start here, for example, with 10, then 30, then 40. So actually I will have a look at this first test case here on my drawing board, and because it's all times 10, I will regard the times 10 factor. So and we'll have a look at this over time. So the first product here would be a 3. Let's say here 0. So 0, 1, 2, 3. Then we have a 1. Then we have a 4. Then we have a 2, 3, 4, 5, 6. Then 2, 6 again, and a 5. Now I can rearrange these 3, I can rearrange these 3, and I can rearrange 3, right? Yes. If I could rearrange all of those, I would just go from lowest to highest. And that would be my optimal value, and from there everything suboptimal is basically I start at 0, right? So I would start like this. If I had to use exactly this order, this would be like my pressure graph moving along, and I would always have to do button presses regarding this difference. So here it would be 3, here it would be 2, 3, 2, 3, 1, 0, 0, 1. But the least number of button presses I have to do is going from the lowest to the highest, which is from 0 to 6. So I have to do at minimum 6. And basically everything that I'm going down, I have to get up again. So if I take the 6 plus all the values I took downwards, which was this 2, here I'm going down, this 2 I'm going down, and this 1 I'm going down. So those are in total 5. So basically from this optimal 6, I took 5 button presses down, which I also had to take back up again. So in total 10 button presses more than the optimum. So this should be 16 in total, which is 5, 10, 13, 14, 15. This one I don't have to take back up again because I ended at 5. So because it was the last operation, it's basically just plus 9. So 2 times 4 plus 1 times 1. I'm thinking if it's optimal just to sort each subgroup. Because obviously I can't sort them optimally, and what I want to do is minimize the downward path it's taking. So in this last group, maybe this could mean, because it's only taking once, not twice. Three. Let's let's think of this formula in another way and do it only for subgroups. So the number of button presses I need for the first subgroup, let's say, is start minus end. The start here for the first subgroup would be 0 and the end would be 4, it was. And then plus 2 times sum of downward values in the subgroup. So if I would evaluate this for all my groups, first group, second group, third group, the first group start is 0. Oh, sorry, it should be end minus start. That makes more sense. No, but I have to check. Maybe this is also only correct. Somehow I need some absolute values here, and probably this sign then corresponds to the sign of downward or upward here. So let's check. For the first step, the end value is higher than the start value, which is here 4. Start is 0, so we have 4 minus 0 plus 2 times the 2 downward. This is in total 8 button presses, which is correct. It's 3 plus 2 plus 3 is 8 button presses. The next subgroup starts at the 4, where we ended up, 1, 2, 3, and ends at 6. So it's 6 minus 4 plus 2 times, we went this 2 first downwards and then everything went up. So this is 2 plus 4 is 6 in total, which is 2 plus 3 plus 1 is 6 indeed. In the last case, we have end is 5, start is 6. So here we would have 5 minus 6, which is negative. Plus 2 times we have 1 downward. And this is actually 5 minus 6 minus 1 plus 2 is actually 1, which is the correct number. Now I'm wondering if this always works like this. So I think this formula is actually correct. Why is it also correct if I go downwards? I'm curious. Let's say I start here, go up, I go down, go up, go down. This would be end minus start would be equal to minus 2. And 2 times sum down would be equal to 2 times 2 plus 2. It's 2 times 4. So this would sum up to 8 minus 2 would be 6. And actually this is 1, 2, 1, 2. This works. And I think the reason is end minus start is just equal to sum of upward steps minus sum of downward steps. And if I add 2 times the sum of the downward steps, then I get the sum of the upward plus the sum of the downward steps, which is just the number of steps. Yeah, so actually this formula is always correct, but you could always do it the other way around, basically saying start minus end plus 2 times upwards or so, or minus 2 times downwards. I think this are all equivalent representations. Why do I think this representation is helpful? Well, because we want to minimize the number of steps, and basically I have a formula now for each subgroup for all the steps, so I want to minimize each subgroup formula. And well, I can, yeah, okay, I think this amounts to this thing. If I add up for all my groups these end minus start values, because the end value of the first group is equal to the start value of the second group, these all cancel out basically, and I have end of my last group minus start of first, and start of first is actually set to 0, so this is equal to end last. This is equal to the sum of all these end minus starts. So we have 4 minus 0 plus 6 minus 4 plus 5 minus 6 is equal to 5, which is exactly just the end value here. Because the 6 cancels and the 4 cancels and the 0 is our starting button position basically. So the green term we can minimize by just making sure that in the last group the value is as low as possible. But then again, the downward steps also correlate somehow with the intermediate values. But again, those cancel out. So, yeah, I'm not really sure how to do this. Let's maybe look again at this first step. I want to minimize this. Okay, maybe I'm looking at this very wrong because I'm trying to think of something greedy, but it might not be a greedy solution at all. In fact, the test set with 1,000 customers, so the large test set here is with 1,000 customers and 100 products per customer. That's actually not that big. It would suggest that it's maybe even something quadratic in n. Probably a dynamic programming solution. And the arguments of my dynamic programming could be something like, let's say after the eth customer, you have a pressure value of x. There are only, after a specific customer, for example, after the first customer, I have only p different pressure values I can have, because one of them had to be the last product I inflated. So yeah, giving my start pressure for one customer, and I also specify my dynamic programming the end pressure as fixed. Basically, I check all the possible start pressures and all the possible end pressures. And for each one of those, I need to compute the optimal filling procedure. And I basically have to check if it goes up the pressure or down. And if it goes up, I want to minimize. Okay, let's do this maybe. Yeah. So I had some customers and I'm at some pressure here from my last customer at this pressure level. Now let's say I have 3 products and they have this pressure level, let's say I have 4 products maybe. These are the 4 pressure levels I need to reach in some order. And in the end, for my dynamic programming, I say so currently I'm going over all my customers, and for each customer I can end at p different pressure values. So if I say I specify this is my start pressure for this customer, and let's say I end on this product, 1, 2, 3, 4, I end here, let's say these are given, and let's say I can compute fast the optimal path through my 4 products to have the least number of button presses, then I need to, of those things, I need to compute n times p squared, because I have n customers going from left to right. And then for each customer, I have p starting values from the previous customer and p different end values from the current customer's products. So there are basically p squared of these start and end pressure values. And so this will be my runtime complexity roughly times the factor I need to solve this thing here. And currently we are here at 10 to the power of 3 times 10 to the power of 2 squared, which is 4. So this is 10 to the power of 7, which is, with combination of 100 test cases and 5 seconds, fast enough. But only if we can do it basically now in constant time. If we can't do this in constant time or in some pre-computed way, then this will be too slow. So this should be probably more like something plus p squared or so. That would be fast enough, for example. And well, what is the optimal way to go through these 4 products? I mean, this product here we had in the end. I just need to visit these 3 levels somewhere in some order. And I want to minimize the button presses. And the button presses is here end minus start plus 2 times the downwards. So I want to minimize my downwards motion. But I have to get down to this level. I think it's always optimal to go in a sorted manner. Basically start with the lowest, then go up. So this would be 1 plus 2 plus 3 plus 2 would be 9. I also could go from highest to lowest, so basically going up, down, down, up. This seems much worse. This is 4. This is 3. This is 2. This is 3. This is equal to 12. I think, yes. So this one was better, going from low to high. Is this actually optimal? Let's try an intermediate path, maybe going first to this one, then down to this one, up to here, and then down to here. This is then, first step is 1, then we have 2 down, we have 1, 2, 3, 4, 5 up, 2 down. This is equal to 5 plus 5, this is 10. Yeah, I think the best thing you can just do is go from lowest to highest, because then you basically get all those steps you anyway need from the lowest to highest, plus these beginning steps and these end steps. And if the second value is lower than the first value, then you need to go from highest to lowest. But the thing you need to pre-compute is basically the lowest and highest values for each subgroup, and then you can actually do it in constant time. So I think this is a valid solution, and it should be fast enough. Very close actually, but yeah, we will try this. Sorry, I hope this gets more clear if I implement this. I think I didn't explain it too well. So the first values we get are n and p. And then we have our vector of pressure values. They're called xaj. So here we have the pressure values. Now we want the minimum and maximum values. I will save this as pair. X-min max. initialize it to the first value. And then we can set x-min max to the mini and maximum values here. And then we can use this array to compute in constant time for dynamic programming the pressure values. So result is just the number of button clicks. I will initialize this to 0, but I don't think it's necessary here. And we need to initialize our dynamic programming approach. So the first argument for dynamic programming is the customer we're just handling. And actually, I'm not sure if I want to save that many numbers, because I only need always for every step the number of button presses, number of minimum button presses for each. Yeah, basically what I'm saying is I only need from the last customer the optimal results for each final pressure. So I only need to record the min presses of the last products. And this will have p entries, and each entry corresponds to taking the last product, the specific product ID basically as last, which specifies my start pressure for the next customer, and then initializes to 0 because my first pseudo customer is basically the empty customer where I didn't have to press any buttons, and I'm starting at the pressure value of 0. Actually, let's initialize this with the first customer. And there the pressure... No, let's do it like this. So I'm looking at current customer N, and I want to update cur min presses. Initialize it with p and infinity. And now I iterate over all the possible end pressure values, which is corresponds to all of the different products coming last. And I need to iterate over all possible start pressure values. So here I have the two for loops over p, so that's where the p squared comes from, and the one for loop over n. But I think that should be fast enough for test set 2, and I just need to make sure that inside here everything happens basically in constant time or extremely fast. Basically I'm only allowed 5 operations, but I hope that I can manage this, because I need to compute the button presses I need, And for this, I need to compare if my from the previous customer xi minus 1 and here I'm now thinking, because I need to reference somehow the first customer. I think what I will do is initialize xij with zeros for the first pseudo customer, having only products which need basically a pressure value of 0. And let's actually do the maximum values also with this pseudo customer, and then I can basically go here from 1 to n plus 1 customers. And xij of i minus 1 is defined. So this is our start pressure. And if this is smaller or equal to our end pressure, which is from the current customer and the kth product, then the minimum min press is equal to x min max of the current customer I second minus x min max from I first. So this is going from the lowest to the highest. Let's compute this here again, sorry. So our minimum here is, let's say this is 3, for example, and this was 4, 5, 6, 7, 8. The highest is 8. So we have from here to here 8 minus 3 equals to 5, and then plus the start values, basically start minus min. So this was max minus min plus start minus min plus max minus end. So start minus min is the first few steps, then max minus min are the steps from the minimum to the maximum, which is in sorted order. And then this downward is again max minus end, which is equal to start minus end plus 2 times max minus min. And actually for the other way around, if the start value is higher, we would go up and then down, 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 and up again. And this would be, the first one would be max minus start plus max minus min again plus end minus min, which would be again 2 times max minus min plus end minus start. And here we had start minus end. So this is basically start minus end absolute value, and then I have a formula for both cases. oh, this is actually minus, because in this case end was smaller than start. So it's like this. And here start was smaller than end. So if I take the absolute value, it actually gets negated, so I need to negate it again. So I should call this maybe x double delta. X double spread. Because this needs to be really fast. So this is actually just 2 times maxi minus mini. So this is now, this whole formula is here as well. And now the minimum number of presses, and I don't even need to this if clause anymore, because now the min presses is just x double spread of my current customer plus, no, minus the absolute value of the start pressure minus the end pressure. The start pressure is xij of my previous customer at level j minus xij of my current customer at product k. So this is now a constant time operation. I mean, here we have one addition, one subtraction, and one sign change through the absolute function. This should be all pretty fast. And now I can say per min presses after level k, after the kth product, is equal to minimum of this and last min presses of j plus the min presses it took me to get from the j previous product to the kth current product customer. So again, here a constant operation and a constant comparison, and those are the only things I need to get the current min presses. And then I just need to save those into the last min presses. And our result then is going over all possible end pressures, just the minimum. Just like this. And it's giving me the wrong result. No, 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 no. Let's have a look at what the current min presses is computed here too. So on the first test case, if we end at 30 pascals, then it says we need 30 presses. The optimal would be from 10 to 30 to 40. And then back down to 30, which would be actually 50. So why does it compute 30 here? the x doubled spread should be 40 minus 10, which is 30, times 2 is 60. So I see how this formula computes to 30, but I don't see where the mistake is. Oh no. So what did I say? In this case, we have the values 10, 30, 40. So the x doubled spread is equal to the maximum minus the minimum, which is 30 times 2 is 60. We start at 0, and I said we ended at 30. And going the optimal path is doing everything in between sorted from low to high. So we would here go to 10 and then up to 40. This needs here a 10 presses, here 30 presses, and here again 10 presses, which amounts to 50 and not 30. Our formula said, oh, this is always for the case where the maximum and the minimum are higher and lower than the start and min. But here this one is actually lower than the minimum. I guess that's the difference here. Okay, so I have to modify this again, sorry. This is then still x min max. Because we need to actually have the correct values here. Mini is then from our current customer. The first value. Start pressure is equal to xaj of the previous customer's jth product, and pressure is equal to current customer's kth product. And the overall minimum is from the deltas, or the x min max minimums, and the start pressure and the end pressure. Let's do the same with maxi. And we take the second value. And now the number of presses is, let's call the start x because this press now confuses me with the button presses. The min number of presses is now, I think, again 2 times maxi minus mini. Is that right? In this case, maximum is 40, minimum is 0, so it would be 2 times 40 minus 0 equal to 80. And then minus absolute value of start minus end, which is here minus 30 minus 0. So this is 80 minus 30, which is 50, which gives the correct results. So again, minus the absolute value of start x minus end x. Let's check if this is the correct solution. Yes, here we get the correct solution. So just to do an analysis on how much compute time this needs. We have here a loop over n, here a loop over p, and here a loop over p, which amounts in this np squared thing, which I computed to be, in the large test case, n is 10 to the power of 3, p is 10 to the power of 2, but squared means 10 to the power of 4. So this in total is 10 to the power of 7. Now we have 100 test cases, which means over all test cases, this is 10 to the power of 9 executions of this inner stuff, which needs to happen in 5 seconds. Now I'm saying everything which happens 10 to the power of 9 times. Basically, if I do 10 to the power of 9 additions, simple additions, this takes roughly 1 second. So if you would do 2 additions, this would roughly take 2 seconds. Now here I'm just reading a value. I hope that is pretty cheap, because actually the compiler should hopefully optimize this and basically directly substitute this value into the start x and end x expressions here. So this is basically, yeah, cheap, I would say. But then I have here a minimum over 3 values, which can't really be optimized that much. So, and I need like 2 or 3 comparisons to do that already. And let's say a comparison is maybe also as expensive as an addition. Maybe it's not that expensive, but let's say this is one addition. Then we have here basically another addition operation, the compute cost. And we have here a third. Multiplication is the same. Fourth, fifth, sixth, seventh. So already I'm guessing that I might be over the time limit of 5 seconds, because this seems like more like 7 basic operations. What I'm thinking now, okay, this end x comparison actually does not need to happen, because the end x is from the ith customer, which is already included in the xmin and xmax computation. So actually comparing with the and value does not need to happen. I can test this again, but I'm pretty sure this is right. Yeah. Yeah, it really might just be in time. I'm really suspicious about this. I'm thinking if there's anything smarter we can do. For example, if I have given my end x value, do I really need to iterate over all start values? And I think I have to do it because there's no easy expression for how the last minimum number of presses over last products factors here in. I can't see how to do it without dynamic programming. I know the solution is correct, I'm just not sure if it's fast enough. And I can't see how to optimize it any further. I could test it now by creating my own test cases with 1000 and 100 values here, constructing some kind of worst case scenario. But I will actually do it in the end and just let it check by Google Code Jam and hope that it's fast enough. It's really on the edge, I think. It might be just a second too slow, but it might be fine. Now, I'm not sure if even the compile time counts into this. I don't think so. I think the compile time is counted extra. You have like some amount of compile time which you're not allowed to overstep, but then basically a new timer is started when the execution of your program actually happens. I think that's how it works. So let's have a look at problem C. ASeDatAb. What? ASeDatAb. Don't know how to pronounce that problem name. Another interactive problem is the hardest one. They really did this year all the interactive problems last, considering it might be the hardest problem. And I actually failed quite miserably on round 1A and the qualification round on the interactive problems, although they weren't too hard, I would say. They were actually manageable. So let's see. The database stores values as records that hold 8-bit binary strings. Unfortunately, the implementation of the function to set the value of a record is flawed. That's bad for a database, I guess. Each record of the database is an 8-bit binary string. Yes. The bits of the binary string are indexed from 0 to 7, from left to right. Okay, when an instruction set a specific record to a new value v is received, instead of setting the value to v, the database does the following. Choose an integer r between 0 and 7, inclusive, and let v be like v but rotated by r to the right. Okay, replace the current value x of the record with x XOR v, the rotated version of our value. That is, the new value of the record has a 1 as its eth bit if and only if the eth bits of x and y are different. Yes. Finally, return the number of bits that are 1 and the new value to the user. Okay. What? Luckily, it turns out that no matter what the initial value is, or what rotation values the database chooses, it is always possible to reset the value of a record to have all bits be 0, with no more than 300 uses of this operation. Implement a program to interact with the database that does this. That means we have at most 300 the record is chosen uniformly at random. Each rotation value is chosen uniformly at random. Exchanges. It's possible to always set all bits to 0, even if the database is adversarial. How do they even come up with those problems? Let's make the problem smaller. Let's say we don't have 8 bits, but maybe 3 bits. Or is 3 already too big? Should we start with 1? Let's start with 1. So, because we are guaranteed that the computer never starts with the 0, we know it actually has just a 1 written in the 1-bit position. What value do I need to plug in so it gets to 0? I guess I can plug in a 1. So let's say x equal 1, v equal 1. Then from this it follows that w is equal to 1 because r is equal to 0. There cannot happen any rotation with just 1 bit. And now we have x XOR w equal to 0. And return 0 because the count of bits is 0. Set bits is 0. And we finish the problem. Okay, so this single bit case is really quite simple. Let's say we have a double bit case. So we don't know if it's 1, 0 or 1, 1 or 0, 1. What kind of value can we use? Because of the rotation, I'm considering to first use v equal to both 1s. So here I get w equal to 1, 1. Because the rotation doesn't change here anything. And now XOR x and w is just x negated. So if x would be all 1s, we would now have all 0s. And we get returned the number of 1s that are set. But let's say we are in the adversarial case. Because we are not finished, this means this can't be 0. So there needs to be a 1. Can there be both 1s? With w being both 1s, that means x would have been both 0s, which can't be. So let's say we have 1, 0, and that means previously x was 0, 1. And we get returned the count 1. But basically now we know that we're in exactly this case. No, we don't know this. We could be also in this case. But we know we're in one of these cases. Now, how can we choose v's such that the adversarial database can't choose a bad rotation? Okay, if we choose 1, 0, then w is equal to 1, 0 or 0, 1. 1, 0 or 0, 1. And then x XOR w, if we have 1, 0 and 1, 0 matching, we would get 0, 0. And if they're non-matching, we get 1, 1. So this can be either 1, 1 or 0, 0. But because we are adversarial, we know that we are now in the case 1, 1. In this case, we can actually handle now again with v equal to 1, 1. And then we're finished. So actually for 2 bits we have a strategy, which just needs 3 steps. can we generalize this? Don't see right now how to generalize it. Let's how complicated does the 3-bit case get? I would again start with v equal to all ones. This is equal to w. Basically, v equals to all ones. V equals to all zeros does nothing. It does not change anything, but we get the count of ones back. V equals to all ones exactly inverts x, always. What other special values of v can we use that do something interesting? I think 1, 0, 0 is the same as applying 1, 1, 0 and then 1, 1, 1. Because the 1, 1, 0 could be rotated to something similar like this 1, 1, 1 and 1, 0, 0, 0, 1, 1. They could be rotated like this. And applying this XOR-wise is the same as applying this XOR-wise and then this XOR-wise, because those numbers basically add up to 1, 0, 0. So we can just look at the case where we activate with v equals to 1, 0, 0. And basically the adversarial bot shifts flips a single bit. Is it maybe that in 3-bit cases the adversarial bot always has a chance to avoid putting all digits equal? Let's say the bot has different digits in x. So maybe 1, 1, 0 or 1, 0, 1, something like this. And now the user comes, and maybe the user puts in all ones, then this number just gets negated to 0, 1, 0, and the bot has achieved its goal. Still, there are different bits, zeros and ones, mixed. If the user comes with like 1, 0, 0 or 0, 1, 1, something like that, then, and the bot has, because it has different digits, there need to be also two same. So let's say this is the same position, or we have it here, the first and the last are the same. And the v also now has to basically the same. Through rotation, we can put these same bits in any position. So let's say we put, so the v is a rotated version, we put the same bits here. Now because of this, whatever we get as a result here, because this number is different to this one, but these two are the same, means that this XOR version, so this is x, this is an x XOR v, means that x and y, these first two are different. Oops, I shouldn't put an error here. The errors meant same, so here it's same, different. So these two have to be different. And comparing the first with the last, these two are different, but these two are the same, so these must be different again, so this must be y. again. But then again, we have one different to the others. So I think with 3 bits and an adversarial database, the database has to report how many bits are set, but it can always make sure that there are 2 different types of bits. So there might be something special about the 8-bit string, and I guess with 3 it doesn't work because 3 is not a power of 2, so maybe it works with 4 bits again. But what is different with 4 bits? Why does my argument not work with 4 bits? Again, let's say the database has achieved different bits, maybe 1, 1, 0, 0. If the user comes with a 1010 string, you can shift this, but it doesn't really change anything in the structure. Then the result would be 0110 would be the same structurally, because x rotated again is the same, because we don't have any control over rotation. So with this v, the user cannot attack this 1100. What if the user uses also the 1100 approach? Again, with all ones, the 0 can't attack, because then we negate and we get the same structure of 2 zeros, 2 ones in some rotated form. 3 ones and 1 0 is, I don't think, interesting. This is 0, 1, 0, 0. Oh yeah, actually that would always produce 3 zeros or 3 ones, I think, because if the database would shift it like this, for example, then we would get here a 1, 0, 1, 1. So in this case, we would have had 3 ones. Okay, let's say, and what is, the database has only a single one? How can the user attack that? Again, this is pretty uninteresting, because we could get 2 zeros and 1, 1. I think anything with 2 ones and 2 zeros is not interesting, because it could always align 1, 1 with the 1, and the other 2 zeros are somehow aligned with the 2 zeros, and there would be another 1, so we would get structurally the same output. So it needs to be either 3 ones. 4 ones is just inverting, which is boring. Inversion is also not interesting. So it needs to be 3 ones or 1, 1. If it's 1, 1, the bot can align it in any way it wants. So maybe like this, and it gets this pattern. Or it could align like this, and it gets the skip pattern. This R, it has to be, it's not the same for all operations, right? Each rotation value is chosen uniformly and independently of all previous. But here, initial value or rotation values as long as it is consistent with all interactions. Yeah, R equals 5, R equals 0. So I see how we can force the bot to get into a 2-bit set position if there's a 1 set bit or 3 set bits, because 3 we can invert to 1 and then we can do the 1 bit attack, and because it can't align the 1 with this one, because then of course we would be finished, means it has to go to some 2-bit set position. So I guess we can always reach a 2 set bit position, but we cannot choose which one. And if we attack this formation with 2 consecutive ones, it doesn't align them, it doesn't anti-align them, because then we would have all 1s which we can invert and finish. So it would be aligning them half-half, which would give us just the same pattern, 1, 0. Oh no, actually it would give us this pattern. So we can actually always force this pattern. Okay. And with this pattern, we can actually attack it with this pattern and finish it. Because aligning them would directly yield 0, offsetting it by 1. Would finish it also. Offsetting it by 1 would of course yield the 1, 1, 1 string, which we can invert and finish then. So maybe in general our strategy is to, if we have 4 bits, our strategy first is to make AB equal to CD. And how can we do that? By because maybe I should say why I think it's interesting to set this as a goal. If we have some kind of operation with which we can ensure that AB is equal to CD, and it seemed we could actually do this, then we basically have a reduced problem set of just 2 bits. Because with any value v, we also do this kind of repetition pattern. I only use these special kind of values now. And if it's this version, or if I rotate it, it would be this version, which is the same as rotating only the 2-bit version. And adding up again gives us some structure AB, or A prime, B prime, A prime, B prime. But if we basically can solve this 2-bit version with a 2-bit strategy for the first 2 bits of V, and we copy them always to the second ones, and at some point we can guarantee that those 2 are zeros in the 2-bit version, then the other A prime and B prime are also by construction then 0. So we just need to reduce our problem to the 2-bit set. And if we can generalize going from 4 to 2, we can try to generalize going from 8 to 4, and then from 4 to 2, from 2 to 1. And 1 is simple, basically. So the question is, how can we force A, B, C, D to become equal? AB becoming equal to CD. So actually always with this, right? If A is different to C, then because we have a 1, 0 and a 1, 0, two spaces apart. In any way we rotate this, it means afterwards A and C are equal. I think the only problem is what is if A is equal to C, but B is not equal to D? Now, because if we attack this with 1, 1, 0, 0, this means A and A here would result in different. So we would have A prime and A prime prime. Those are different, but B and D, they were different. So they are now B prime, B prime, they are now the same. And then we would have again the same structure as here. What if we attack it only with the single one? With the single one, it could either make the B equal to D, or it could make the two A's different. Can we distinguish those two cases based on the count of bits which are set? Basically, this is always an odd number of set bits because A and A is the same and B and D is different. So these basically have an even number of set bits and these have an odd number of set bits. So the total number of bits is set is odd. And applying a 1, 0, 0, 0, 0, so flipping one bit of those would yield in an even number of bits, which would mean the two A's and the B and D are equal pairwise, or they are pairwise different. If they are pairwise different, we need to apply this here. And if they are pairwise equal, we can do our reduction. And how can I generalize this thinking to 8 bits? That seems kind of crazy. Can someone make this reducing, making the first string equal to the second one also somehow recursive? Is that even possible with 8? I mean, a different approach, a very different approach, would be to somehow construct all the possible sets for the initial x, which is 2 to the power of 8, which is actually not that much. It's just 256 different possibilities. Actually, minus the 0, 0, 0, 0, it's only 255. And then construct, based off of this, some v which minimizes the number of different output combinations. So that they all collapse to 0, under the assumption that the adversarial never returns zeros. So basically I have 2 to the power of 8 different x values. I can check all the different v values I can plug in, which is basically also 2 to the power of 8, but divided by some shifting. There are only a few unique ones actually, because I have no control over the shift. So it's more like 2 to the power of 8 divided by roughly 8, because there are 8 different shift positions. But of course all ones or all zeros can be shifted. Yeah, so it's maybe roughly 2 to the power of 5 or 32, roughly speaking. And for all x's and for every v, I could take this whole x set, transform it into a new x set, checking all different rotations. And then from all of those, I could take the one with the smallest count. Does it then always have to reduce the count? And how in the end, if the count is 1, how do I still get to the final position? Because if the count is 1, there's only one x value left that's possible. But then I think there's directly, I can just check the set bits and minimize those or maximize those. Let's say I've reduced it to this x possibility. I'm not even sure if that, no, that cannot be, because of all rotations, it means I would also have this x possibility and yeah, all those 4 different ones. So it would be actually less if it's some form of symmetry. So this would be actually less possible combinations. And then applying zero, 1, 0, 1 would reduce this set to just all ones. Because the 0 case is of course the one I always assume will not happen in the adversarial setup. So maybe this is actually and I think the runtime is 2 to the power of 8 times 2 to the power of 8, because I have to check every w and every x combination pair and do some computation, which is the XOR operation, which is quite cheap. And this I have to do 300 times, because that's what the problem says is the most number of steps. 2 to the power of 16 times 300 is roughly 2 to the power of 10 is 10 to the power of 3. 2 to the power of 6 is roughly 64 times 300,000. 300,000. This should be fast enough. I will try to implement this. Not sure how this might look. Okay, welcome back. The Google CodeJam server actually now processed my solutions. I submitted them right after the contest, and you see Pancake went through, and even the controlled inflation went through for the large test case. Sadly, it doesn't show me how long it ran, but it seems it was fast enough. Let's actually have a look at the analysis and see if the dynamic programming approach was the one they also took. It seems so. Do they do some kind of computational analysis? I think they found even another insight why the last pressure should be either the highest or the lowest of a sequence. And then it's, of course, you don't have to iterate over all the p-values, but only the 2 and the 2 before, which I think makes it here basically a n times 4 instead of n times p squared. But yeah, the problem statement was formulated with p of 100, and that seems to be fast enough to work with p squared even. So now to the interesting interactive problem, which I could not solve. I tried a bit around, but actually I think I will cut this out of the video, because yeah, it was quite terrible, I must say. Anyways, as I suspected, you could actually advance round 1 here by just solving the smaller part of this test set, which is basically not smaller, but it's not an adversarial, but a random database. And here you can really take the probability approach, do a lot of attacks basically to the database, and increase your probability after some time that you will hit the 0, 0, 0 by doing it somewhat strategically, but not like a superhuman idea to get this. So the adversarial database, of course, is much harder. And the first thing they explain here is that the number of states is actually not too big, and you can enumerate all of those when you consider rotations to be invariant, basically. Then there aren't that many. For example, if you look at all the sets where 2 bits are set, then these 2 set bits can be directly next to each other, or with 1 space, or with 2 zeros, or with 3 zeros, but not more, because otherwise you, well, if you have here 4 zeros between the ones, then there's another space with 2 zeros, and those are rotationally the same, basically. And then you can see that actually even in the 4 bits case, which is of course the one with the most different permutations, there are still only 10. And you can really do basically a graph for all the different possibilities the database can currently hold, denoting a set of possibilities as a state, and then computing for all possible states, which are then 2 to the power of 10 just for the 4-bit case, computing basically all other states you can reach. You get basically a graph of how this game with the database plays, and you can do a breadth first search, basically starting backwards then, of course, from you want to reach 0, how can you get there from other states, and work your way back to the initial state where basically all possibilities are included in the current state. But I would say that's quite complicated to implement. Not the easiest, of course, at least. You would by hand enumerate all these different states and take care of these different cases where you get reported different bits. And actually what's quite interesting, they say there's an alternative approach, and I tried something like observing some rule which I can use to construct some pattern to apply to this database. And that actually does not require to observe how many bits in the database are currently set. And I was actually thinking in this direction, so I can show you my notes here and try to explain how this works actually, because it's not well explained in an analysis and it took me quite some time to understand it myself. So I tried first with only one bit, what happens there, and of course it's quite easy because you can say the adversarial machine starts with 1 and not 0, because otherwise you would be finished before you even started. And with the 1 you can just say yourself as input value the 1, and then it gets negated and you have the final case. And then already if you start to look at 2 bits, they cannot be both 0 because again you're finished before you started. If they are both 1s, you could set your values to your value to both 1s and negate it to get to be finished. So you can do basically this. Then again you can conclude that you're in the 0, 1 or 1, 0 case, because again both 1s is now excluded. And in this case you can apply a 1, 0 or 0, 1. It gets rotated either way. The W is 1, 0 or 0, 1. And the XOR version is then 1, 1 or 0, 0. But again, in the adversarial case, you would be in the 1, 1 now. And now you can apply again the 1, 1 case. And now I actually erased this here, but I found out that actually with 3 bits, the adversarial database can always prevent you from getting all zeros. So if you're playing against the devil, you would not stand a chance. I found that quite interesting. So I thought, okay, maybe it's only working for powers of 2 bits. So it works for 1, for 2, not for 3, but then for 4 again. And what I experimented a little bit with 4 numbers. Actually, you can see here, some operations I tried. And an interesting observation I then made is, if you have basically 4 bits and you know the first 2 are the same as the last 2, then you can apply your operations you used for the 2-bit case, but always like copied. So we did here first a 1, 1 to make sure these 2 are different. Then we made 1, 0 to make the 2 different bits the same. And then we again applied 1, 1. And if we know these 2, so if we have the pattern, let's start on the page now. If we have the pattern AB, AB in the 4-bit case, then we could again use this 1, 1, 1, 0, 1, 1 combination and copy it back to this row here. Because even if this gets rotated 1, 0, 1, 0 by the bot, it could only become again 1, 0, 1, 0 if it rotates over our 2-bit boundary, or it gets rotated to 0, 1, 0, 1. But if we split again in the middle, 0, we have again this half string rotated, which is the same as just rotating this 1, 0. So we basically reduce this problem to 2 bits as soon as we have AB is equal to AB. What I then couldn't figure out, and which is not really well explained here, is how do you make sure at some point that these 2 are the same, so that you can apply the one lower dimensional basically sequence. And I think I'll try to explain this now, how I come to understand it. Now, what you can look at is basically, they call this here P of K, is basically a sequence of operations which solves the test case for T to the power 2 to the power of K bits. So P of 0 is just the 1 sequence, because we have just 1 bit and it's set to 1 and we need to invert it. In the P1 case is then already this 1, 1 to check that they're different, then 1, 0 to making them equal, and then 1, 1 again. Now, what we need is P of 3, of course, and we want to go via P of 2 maybe. What we can look at is, let's define x hat as x first half. So if we have our current x with 2 to the power of k bits, then we have a first half and a second half of bits, yes? Maybe like this in the 8-bit case. And we would call this now x prime and this x prime prime. And we have, and let's define x hat as x prime XOR x prime prime. So XORing these two. Now, so we are in the k case, yes? So we basically already have, by principle of recursion or induction, we have already our sequence pk minus 1. What happens if we take this sequence and every step we copy basically, so we have here our elements Si, and we can take as our current, our new sequence, big Si is just small si concatenated to small si. Basically, I don't know how to write this as a plus. It's a concatenation of the bits, yes? And well, the question I'm trying to answer now is what happens to x hat in every step. So in every step I have x, I apply my sequence, and I have a new x, and I also have a new x hat defined by this rule, taking first half XOR second half. And I'm asking myself, well, what happens to x hat during the appliance of my sequence for the case k minus 1, and if I double it like this? So if Si has at some point bit set, then because of the concatenation, this bit is also set 2 to the power of k minus 1 positions further. So basically in the case of k equals 3, there are like 3 zeros here in between, or 3 anythings really. But then there's again this one is from here and one is from here. So what I'm trying to say is this representation, if I line it to my 8 bits from this x prime and x prime prime, it could be like 1, 1, 0, 0 maybe. And then we have the same as I 1, 0, 1, 1, oops, let's align it correctly, 0, 1, 1, 0. But again, this Si can be, so this is of course then our value, which we put into the database. But the database can rotate it, of course. But if it would rotate this, it would still mean that basically we have this pattern again here. So if we rotate this, for example, I had the 0, 1, 1, 0, 0, 1, 1, 0. If I rotate it by 1 to the left, it would be 1, 1, 0, 0, 1, 1, 0, 0. So you can see still we have always this form of concatenating. Even if it gets rotated, it still looks like the same here and here. And then if we XOR this on the X, it's basically as the operation we then perform on X hat is basically here X prime, so X hat after is equal to X prime XOR SE, and this is XOR X prime prime XOR SE. And because the XOR operation is associative, we can remove the brackets, and it's even commutative, so we can rearrange the terms, and we get actually that it's equal x prime XOR x prime prime XOR SE XOR SE. But taking number XOR itself is always 0, and 0 XORing with something is always the identity basically. So we can always remove XOR 0. So we actually get that the x hat afterwards is the same as the x hat before. What is the story of this? If we apply our sequence of k-1 on this on the string in this doubled version, the x hat will never change. Now we have two cases. The first case is x prime and x prime prime are the same. That means x hat is actually equal to 0. It will never change during the sequence, but actually during the sequence now we have guaranteed, like I tried to explain this in the beginning, if we have this AB pattern and our previous sequence, it will now make both of them at some point equal to 0. So in the case x prime and x prime prime are equal, this pk-1 sequence will make them both 0 at some point, and they will be 0 the same at the same time even. So we're finished, and because of course our database is adversarial, this means actually before we even start this, it won't be that those two are equal. That means the x hat will actually be not equal to 0, but we want to get there at some point. And what we want to basically do is now x hat is actually also a version of 2 to the power of k-1 bits only, right? So again, here we have an 8-bit number, but x hat is only a 4-bit number now, because it's this reduction of this half. So we can also apply this pk-1 sequence on this x hat. And from this instruction here, how we computed x hat after, you can actually see we can do this by not concatenating Si with Si itself from the step of pk-1, but Si concatenating with zeros, as many as you need. So in this case, because we have 8 bits, we would concatenate 4 zeros instead of the 4 bits of Si. And then, so basically this is then the 0 number. And then x after would be x prime XOR x prime prime XOR Si. And x prime XOR x prime prime is our previous x hat. So x hat after is basically previous x hat XOR Si. Now you have to think here again about the rotations. What happens if I rotate this Si and the 4 zeros around? Then of course it could be like 0, 0, 0, 0 Si, or something like 0 Si, 0, 0, 0. And how does this affect x hat? And it is still actually that, I mean, Si itself can be rotated in itself, and that would be fine for our pk-1 sequence, right? So this is actually, if you apply it here, you have 1, 0 here, then the 3 bits of Si on the x prime, and then the first leading bit of the Si on the x prime prime. So it basically still works like this, with the Si being rotated basically by 1. So if I go from this to this, it's basically a rotation by 1 with zeros, but in the 4-bit space, it's also a rotation by 1 with the Si. And because our pk-1 sequence is guaranteed to work with rotated Si's as well, or being safe regarding those adversarial attacks from the database, this makes it actually so that if we apply this, we can actually go through all the x hat values and at some point guarantee that x hat is equal to 0. The only thing in the reduction we're doing now is actually after we applied one step of our pk-1 sequence with these zeros, we don't know if we have already reached x hat equals to 0. But if it's 0, we have not actually directly won. It just means that the first part is equal to the second part. So after every 0 SI instruction, we need to again do all of pk-1 instructions in this SI plus SI format. And then we have basically ruled out that x hat is 0. And then we can do again the next step of the 0 SI steps to get our x hat closer to 0 basically. And at some point, because the pk-1 is constructed in this way, at some point we need to reach the x hat equal being 0. And if we in that final step again apply our pk-1 sequence in this doubled way, then at some point we also have the case where all bits are actually 0. And again, the quintessential observation here is if you apply the pk-1 sequence in this way, x hat will actually never change, right? Because here the Si cancelled with itself. So that means after performing these operations after such Si plus 0 operations means we're basically at the same value x hat as before, and that means that these outer operations Si plus zeros see an unchanged state basically. And that's why they still work. Yeah. I hope that got kind of clear. I didn't implement it now. I will do it later. I don't know when. Here's just the Python code that actually constructs the sequence. So basically you just need to apply those sequences then in the end. You could also compute how many sequences this will be. So you can actually see here how this P1 gets constructed from P0 from what I said earlier. You apply the sequence pk1 in a doubled manner, this is just P0 doubled, 1, 1. Then you apply it once with zeros appended, which is this. So this is basically the 0 appendage. And then you apply again the double version. And P of 2 would then be double all of this. So it would be 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1. So I've doubled all of this. Then I need to take the first instruction with zeros, which is 1, 1, 0, 0. So the 2 1s with 2 zeros. Then I need to again copy all of this here. Then I need to take the second instruction, 1, 0, and append zeros to it, 0, 0. Then again, I need to do the doubled instruction here. And then for the last, I need to again take 1, 1, 0, 0, and again, all the doubled instructions. So this is just one operation. These are 3 operations. These would be already 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 operations. And you can see already the number of operations here. It's actually because of all this doubling, it's 2 to the power of k plus 1 here and minus 1 here. So 2 to the, for k equals 0, it's 2 to the power of 1, which is 2 minus 1 is 1. Here we have 4 minus 1 is 3, and here we have 16. Oh no, it's actually 2k. No, I'm not sure. Length of K is equal to all of these operations with the zeros, which is just P of K minus 1. The length. Let's take absolute bars here for the operation length plus these square brackets. We have actually pk minus 1 plus 1 time plus 1, and that multiplied with the length of pk minus 1. So the 15 is actually 3 plus 4 times 3 is 12 plus 3, yes. And P of 3, the length would be then equal to 15 plus 16 times 15. Which is 16 squared actually. No, which is 15 times 16, yes. 15 times 17, which is 16 squared minus 1. Okay, that's the formula. Take the previous value, add 1, square it, subtract 1. So 1 plus 1 is 2, squared 4 minus 1 is 3. 3 plus 1 is 4, squared is 16, minus 1 is 15. 15 plus 1 is 16, squared minus 1 is the number of operations you need for 8 bits, 2 to the power of 3, which is actually below 200. No. 16 squared is 256, yeah, it's 255. Yeah, so that's our number of operations you need. I hope this helped. I think the first two problems were very easy, and you can actually see in the scoreboard, again, if you check how many points you needed to be top 1000. Oh no, actually you can be top 1500, right? But you still needed a small test set in actually under 1 hour 44 minutes to advance. So I think it was quite a tough round. If you managed to get the points, congratulations. Here you can really see it, that it helps a lot if you maybe just go. I think a lot of these just went for the small test case. They knew they wouldn't solve the large one, but it was actually enough, because if you look at the number who solved actually the large test case, was just 1%, or 133 of the contestants. That means from the top 1500 contestants, basically all of them just solved the smaller one here. Yeah, so in total 2300 solved the smaller one here, and then some of them didn't solve the first two or were too slow. But yeah, I think if you focused early on just solving the small one, instead of going for the both ones, the large one as well, and not solving anything in this competition, it paid off. So if you remember, if you didn't manage to get it in this round, you still can participate in round 1C and get in the top 1500 to advance to round 2. So I would really encourage you to give it another shot if it didn't work out this today. And hoped I could help with my explanation, especially to problem C, a bit better to understand how one could approach this. But I think it was a quite hard problem this time, actually. I said the previous interactive problems I didn't solve, but afterwards I thought they were quite easy. I would consider this one actually quite hard. Yeah, so thanks for watching, and don't forget to subscribe and like. See ya!